We're going to be looking at the PDP-11 architecture, a classic mini-computer architecture that was released in the late 60s, and its architecture is extremely interesting. But before we do, we need to look at the issue of Bigendian versus Littleendian storage of data. The PDP-11 is a 16-bit machine, which means its word size is 2 bytes, 16 bits. It's also a byte addressable machine, so you can address bytes or you can address words. If you address words, the words are always on an even boundary. Bytes, of course, can be on any boundary. Now, in the PDP-11, unlike the mainframes at the time, the way the data is stored is in Littleendian form. Now, this is the Wikipedia page on Endianness, and we have the two examples right here. Now, these examples are for 4 bytes of data, 4 bytes of integer, but works with 2 bytes as well. So we have here the same 4-byte integer number, and it's in hexadecimal, 0A, 0B. Each of these 2 digits, hex digits, of course, is a byte. So altogether we have 32 bits, which is 8 hex digits. So this is the high order portion of the number. This is the low order portion of the number. All right. In Bigendian format, okay, here's the memory. A is the address. Address plus 1 plus 2 plus 3. There's 4 bytes. In Bigendian form, the high order byte goes in the low order address. So the byte addressed in a 32-bit or 4-byte integer on a Bigendian machine is the high order byte. The low order byte goes in the last byte of the word addressed in memory. So this is Bigendian. The big value goes at the location addressed. In Littleendian, it's just the reverse. In Littleendian, the low order byte is the byte addressed. So in other words, when you address a word in memory, you give the address of the first byte, and it's that byte plus the next one plus the next one plus the next one if it's 4 bytes. In the case of 2 bytes, of course, it's only that plus the next one. But in Littleendian format, the low order byte comes first, and then you go to successively higher order bytes until you've stored them all. So the byte addressed in Littleendian is the low order byte. In the byte addressed in Bigendian is the high order byte. Makes a difference. Now, at the time the PDP-11 was released, the main machine that was in circulation, there were several mainframes in those days, and not very many mini-computers. DEC, Digital Equipment Corporation, pretty much owned that category. But the IBM mainframe, the 360 series, which was around at that point in time, was Bigendian. And DEC came along and went with Littleendian. The Intel architecture is Littleendian. The IBM mainframes are still Bigendian. There's actually some advantage to going with Littleendian. People back in before the days when you had strict parameter checking to subroutines, if you had a 16-bit integer that you were passing to a subroutine, well, the subroutine's expecting 16 bits, but you passed it, let's say, 32 bits, which was easy enough to do in Fortran or even PL1. If you passed a 32-bit integer to a subroutine expecting 16 bits, the subroutine would see the 2 high-order bytes as the 16-bit value, and that was not good. In Littleendian format, you can make that mistake, and it won't hurt you. In that the 32-bit number that you're passing, well, the 2 low-order bytes are going to be the 2 bytes that the subroutine sees as the integer. Now, your program's still wrong, but it's not going to be as catastrophically wrong. There's some degree of latitude there. Nowadays, these things are checked. Data types are checked, and we don't really have that problem unless you deliberately override the system. But anyway, I did want to mention that we're talking Littleendian when we're going to be dealing with the PDP-11, because that makes a difference as to how we view the memory. The PDP-11 was a 16-bit mini-computer sold by Digital Equipment Corporation from about 1970 until the late 1990s. There were actually East European clones of it in that period. In total, according to Wikipedia anyway, 600,000 units were sold. It was certainly one of DEC's most popular models, and as mini computers go, it was probably the most popular ever. everyone liked the PDP-11. It was eventually replaced, so to speak, by the VAX-11, which is a virtual address extension. It was a 32-bit machine, but borrowed many of its architectural ideas from the underlying PDP-11. As a matter of fact, the VAX-11 had a PDP-11 compatibility mode, so you could actually run PDP-11 software directly on it. The instruction set was quite innovative. It had multiple general-purpose registers, which was not common in those days on small computers. It had a very innovative unibus, which allowed you to quickly plug in new peripherals and access them immediately with just a few settings and so forth. It replaced, as it mentions here, the PDP-8, which was also a very popular machine, but it was a 6-bit character machine. The PDP-11 became the choice for many real-time applications. It was the workhorse in many universities for many years, both in laboratories and in computer science departments, where they ran Unix on it, it was also used for time sharing. There are a number of operating systems written on it, from the very basic RT11 to RISTIS-E, RSTS/E, which was a time sharing system, RSX11, which was a real-time system, and others. As it mentions here, it inspired the design of things like the Motorola 68000 and MS-DOS and CP/M. Actually look a great deal like RT11, suspiciously so. It came in a variety of, there's a picture here, as you can see, of an 1140. This would be the actual system console down at the bottom here with all the switches. The switches were, most of the switches were address switches. You entered in an address by playing with those switches, turning the bits on and off. And once you entered an address, you could enter 16 bits worth of data. And there were various other switches here. You could actually enter small programs. And on the lowest end models, very often you entered the Bootstrap program that way, or a similar way. So that's the basic console there. These are some DEC tapes. They were a type of magnetic tape peculiar to digital. They were a direct access magnetic tape. They were pretty good. This there's no visible disk drive on this one, but they did have disk drives. Depending upon the model. Some of them got quite large. The original version of it was, of course, 16-bit, which meant it only had a maximum address space of 64K. Sounds ridiculously small by today's standards. But in the later models, they added what they called virtual memory that allowed multiple address spaces to be in memory simultaneously. I don't know what the top end on memory was, but it was quite large in later models. It was an excellent architecture. I had one once. I had a PDP-1103, which didn't use the Unibus. It used something called the QBus. QBus was like the Unibus, but it was cheaper. Data and address shared the same lines, so it was slower as well. It was very suitable for small office applications, that sort of thing. Anyway, this is the machine we're going to look at, and we'll get started. This is an overview of the architecture of the PDP-11 as it existed in 1979. This is from the 1979 handbook, which is available out on the internet. If you Google for PDP-11_handbook 1979.pdf, you should find it. And it's a very large PDF. It gives an overview of the models as they existed then. I'm sure there were probably some changes here, but by this time the VAX-11 780, 1978, had come out. The low end was the LSI-11, the 1103, that sort of thing. There was an 1123. It's not mentioned here. It was probably later. It says sub-Unibus. That was the QBus. It was the cheaper version of the Unibus. It didn't have separate address and data lines. They were shared. These were. I had one of these. They were relatively small. They were very competent machines, though, implemented on a couple of LSI chips. Then you went up to the Unibus machines, starting with the 1104 up to the 1160. These are how they named their models. Higher model numbers were generally higher performance. These were all Unibus machines. The Unibus had separate address and data lines. The high end of the Unibus, if you're looking at the basic 64K address space, the top 8K of a Unibus machine was for devices. Anything above 54K was a device. In other words, most of those memory addresses didn't exist because you didn't have 8K devices. So whatever number of devices you had, that would be they would be memory locations in that address space. But otherwise, the addresses above 56K were empty. On the LSI 11, that's where there was a difference. The address space was the top 4K of bytes. And so technically they were different in that regard. An LSI 11 program might assume a 60K usable space, whereas that wouldn't be true on a basic Unibus machine without any extended memory options, which they did have in later models. Then you go up to the 1144 and the 1170, and they introduced some additional bus architectures. And then you went to the 11780. There were number of models there. There were some Unibus. SBI was I think the more common system bus interconnect, I think it was called. But basically speaking, it was a compatible line of computers across a fairly large range. And as we mentioned before, it was manufactured for about 30 years. And there's probably some of them out there running to this day. Here is the general layout from the 1979 manual of how the architecture looks. You've got the Unibus. And into the Unibus, you plug everything, including the CPU gets plugged into the Unibus. Disks get plugged into it. Line printers get plugged. Well, the interface card, not the line printer itself, but the line printer is plugged into the interface card. So you'd look inside of a PDP-11 machine, and there would be a bus down there, and there would be cards plugged into it. And those cards were the various things you're seeing here. Core memory was plugged into it, all sorts of various devices that were plugged in, and for the most part, many of the devices were all mapped into high memory. Memory, of course, was memory. So that's how they were plugged in. The CPU, of course, being the CPU, it kind of had a special place on the Unibus, obviously. But it was plugged in. Inside the CPU, the layout is there's an arithmetic and logical unit which does all the processing. There's the processor status word, which contains various bits, including the condition code, the current priority level of the machine, used in terms of processing interrupts, and bits that indicate whether it's in supervisor or kernel mode or user mode. And then there were 8 general-purpose registers. And the general-purpose registers are available, of course, to the arithmetic and logical unit. The registers are kind of general until you get to register 6. 6 and 7 are actual registers, but they have special meanings. Register 6 is the stack pointer. It's used by a number of addressing modes and operations to manipulate a system stack. This was relatively unique in its day when it was originally introduced. And we'll see the stack pointer in use and stack pointer addressing later on. And number 7 is the program counter. That's the address of the next instruction to be executed. That is every time you load an instruction into the ALU, Arithmetic and Logic Unit, and before you execute it, the program counter is updated to point to the next instruction. The instructions, for the most part, are 2 bytes in length. However, they can have additional material, additional words added to the end of them for some of the addressing modes. The longest instruction on a basic PDP-11 could therefore be 6 bytes long, 3 words. Words are obviously 2 bytes. So this is the overall layout of all of the entire architecture. It was very simple, very straightforward, and very functional. The data formats on the original model were either byte or 16-bit word. In later models, they added additional data types for floating point, for 32-bit operations, a commercial instruction set, and so forth and so on. The page you're seeing is, of course, from Wikipedia. The bytes, of course, can appear on any address, 1000, 1001, 1002, 1003, so forth. The words, however, had to appear on even addresses, so 1000, 1002, 1004, and so forth. When you addressed a word, the byte addressed was the low-order byte. It contained the least significant bits. The second byte, the byte at address +1, contained the high order bits. We mentioned that in the discussion of Littleendian and Bigendian. The basic address structure on a PDP-11 is a 16-bit word. That means the machine can have, theoretically, 64 KB. Now, in later models where they had memory management, they had much larger amounts of memory. But the basic, this original architecture, and even the later architectures, there was always 16-bit address. But memory management may have supplemented that to page you someplace else in memory. But let's just stick with the basic 16 bits. That maps to 64 kilobytes. We often don't refer to it as kilobytes. We refer to it as words. So that's 32K words. All right, not all of that can actually be memory. Some of it is memory-mapped I/O devices. On a unibus-based PDP-11, that was one of the two buses they used. It's a bus you plug in memory, you plug in devices, you plug in the CPU, and it's the interconnect. It was kind of revolutionary for its time. On the basic unibus machine, the top 8K of the address space was reserved for devices. So if you plugged in a printer, the printer would be someplace in that address space. There would be words in memory that were actually on the printer card. So if you wanted to write to the printer, you went to that particular address and you put data there and control information, and that would cause the printer to do stuff. Okay, so the top 8K on a unibus machine was available. It didn't have real memory. There was not regular, in those days it was all core memory. There was semiconductor memory hadn't come along yet. But there was no core memory between 56 and 64K on a unibus machine. That was reserved for device vectors, for devices, and the memory there was actually on the device. So it was mainly empty. The top 8K or 4K words was essentially empty. There would be only 10 or 20 devices on even a large machine. Everything else was empty. Now, there was an exception. There was a LSI-11, which was a PDP-11 on a chip. It was a microcomputer version of the PDP-11, and it was sold as the 1103, and I believe there was also an 1123. But anyway, it did not use the unibus. It used something called the Q-bus. Now, on the Q-bus, it was only the top 4K that was used for to memory map the devices. So in a Q-bus machine, you could have 60K of actual core memory, and only the top 4K was for device addresses. I actually had one, so I know it was 60K. Anyway, the PDP, the microcomputer version, the LSI-11, was really advanced for its time. And it was out in the late 70s. And had they played their cards better, they, rather than Intel, would have become the dominant mini computer, a microcomputer vendor. But Digital didn't play their cards right. They wanted to hold the world ransom, and they made their products extremely expensive. And as a result, they eventually disappeared. There was a lot of mistakes made during the 80s, the early 70s, and going into the 80s. But they certainly had the right product. All right, the low addresses. Oh, the other thing here is everything's in octal. I know it's a 16-bit machine, and hexadecimal would have made more sense. IBM was using hexadecimal in those days. IBM was a 8-bit byte. A lot of machines back then in the late 60s, mid to late 60s, were still octal-based machines. They were based on a 6-bit character, and you would have 2 octal digits in a 6-bit character. Now, a 6-bit in three bits, you can count from 0 to 7, which is octal. Much like in 4 bits, you can count from 0 to 15, which is hexadecimal. But a lot of the 6-bit character machines were still around, and even but they decided to use octal in all of their notation. So when we look at these things, we'll see octal everywhere. You can see some examples here. The address 1, bunch of 7s, subscript 8, it's an octal address. So most of the numbers are going to be octal that we will see. It makes sense up to a point because things like the number of registers and the number of addressing modes and so forth, these are in fact 8 in number. So it works out. But it does create a problem when you have like a byte and you've got 2 octal digits, totaling 6 bits or 3 bits apiece, and you get 2 bits left over. So to represent a byte, you use 3 octal digits, but one of the octal digits is constrained. It can't get to 7 because it's only got 2 bits. Anyway, that's how they did it. In the low memory, which actually was real memory, this was reserved for vectors, for interrupt vectors, and it would and each vector would consist of a processor status word and an address to be loaded in as the program counter, a program counter value. So each interrupt vector consisted of a processor address and a processor status word. And what would happen is an interrupt would come in, and the interrupts were vectored, which means they knew where to go. So an interrupt comes in from a device, and it puts an address onto the bus, and it knows where in low memory to go. And the interrupt mechanism grabs the value of the program counter, and it grabs the value of the processor status word and loads them into the program counter, the real program counter and the real processor status word, and simultaneously saves the contents of those. So you save whatever was going on, and you now branch a vector immediately into an interrupt handler. So that's how interrupts work. But basically what I'm saying here is the low addresses on a machine were used for vectoring interrupts. Now, interrupts could occur because a device, for example, a printer is ready. For example, a keystroke has been made on a keyboard. A disk has finished doing whatever it was doing. It could be a hardware error. Any number of things can cause a hardware interrupt or trap. Or you could have software errors. Certain types of software errors, a bad address and things like that would generate traps or interrupts. Or you could actually execute an instruction which would generate a trap. As you see some of the instructions there, BPT, EMT, IOT, and trap. These are instructions which actually generate interrupts and cause things to happen. And the things that happen, for example, if you want an operating system service and you're running in program state and you need to go to system state, you generate a trap which causes the operating system to become active. You go into operating system state, it does whatever you asked for it to be done, and so forth and so on. It's built into the architecture. So that's the basic idea on memory. 16-bit addresses, maximum real memory, 56K on the Unibus machine, 60K on the QBus machines without memory management. Actually, the QBus machines I don't think had memory management. It's only the Unibus machines. I'm not sure though. And we've got the low memory is reserved for vectors. Now we come to registers. The machine had 8 registers, cleverly numbered 0 through 7, but they weren't always called that. Registers 0 through 5 were general-purpose registers. They were 2 bytes each. They're integer registers. You can use them for byte operations. They are general-purpose registers. Register 6 is also called the stack pointer. Some instructions refer to a stack or use a stack. This is where they get it. There is a built-in system stack pointer. It's either referred to as register 6 or as SP. That's the notation in assembly language for the stack pointer. Okay, so that's one of the registers you don't play around with. The stack pointer you don't want to mess with because it'll be maintained. For example, you call a subroutine. On entry into the subroutine, data is allocated, local data for the subroutine, and it's allocated on the system stack. And the stack grows down from high addresses to lower addresses and so forth. It's part of the operating system and the hardware. Now we'll see the instructions that use that too. Register 7 is also the program counter. It contains, which is either R7 or it's PC. PC is probably more common. It is the address where it will fetch the next instruction from. It is the program counter. Instruction address sometimes called, but the program counter, it tells the machine where it will pick up the next instruction. Now, there's some odd addressing modes that we'll see that actually use the PC plus local data to create an unusual form of reentrant code. Additionally, we have a processor status word. The processor status word contains the bits that indicate if there's been a carry, if there's been an overflow, if the result was 0, if the result was negative, if a trap has been executed, and it also contains the current interrupt level of the machine. That determines whether or not new interrupts can come in. New interrupts come in and they are of a value lower than this. They pend, they wait. They can only interrupt if they're greater than this value. And you have the floating point status register, but that came much later, so we're not going to talk about the floating point status register. It didn't exist in the early machines. All right, now we're going to look at addressing modes. In a PDP-11, an address is specified with 6 bits. 3 bits indicate the addressing mode, 3 bits indicate the register. There are 8 modes, 0 through 7, and there are 8 registers, 0 through 7. All right, mode 0. Now, what this table is, here is is what it would look like. The first digit here indicates this is decimal digits, by the way. Well, I guess they're octal. You know, we don't go above 7, so it's the same for decimal or octal. This is the mode number, 0 through 7. This is the addressing mode. The second thing here, indicated by N, that's the register number, also in the range 0 through 7. So 3 bits and 3 bits, 6 bits altogether. This is the name of it. Each of these has a name: register, register deferred, auto increment, and so forth. And then this is the symbolic assembly language format that would be used for this particular addressing mode. And finally, there's a description of what's going on. In mode 0, the register is the operand. So the operand is contained in the register. I'm manipulating the register. So that's the simplest form. Register deferred says that the register contains the address of the operand. The operand is in memory. The register points to where in memory. So we go out to memory and we work on the operand there. Now the operand can be a byte operand or a word operand, same as the previous one. That depends upon the instruction. Some instructions are 1-byte instructions, some are 2-byte instructions or word instructions. We'll look at those later. Then we got auto increment, or mode 2. In auto increment, the register contains the address of the operand. So the operand's out in memory. Might be a byte operand, might be a word operand. And then we increment the register. How much do we increment the register by? I don't know. Depends upon the instruction. If it's a byte instruction, we increment by 1. If it's a word instruction, we increment by 2. So it increments the register. And the amount of the increment is determined by the actual instruction. So if it's a byte operand, we increment 1 or 2. If it's a word operand, this would be used for a table. If I had a table out of, say, of words out in memory and I wanted to add them all up, this mode here would allow me to add one of the words from memory, let's say, into another register, and then automatically move to the next one. So it not only addresses the operand, but advances to the next one. It's really good for tables and arrays and things like that. The next one is auto increment deferred, mode 3. The register contains the address of the address, and then it is incremented by 2. The register is incremented by 2. So the register points to a word out in memory. That word is the address of the operand. So we go out to memory, and then we hop someplace else in memory. The actual operand is further down the track, as it were. And then we increment by 2. Why 2? Why not 1? Because we are incrementing to the next address out in memory. This assumes that out in memory we have a table of addresses. 2 bytes for one address, 2 bytes for the next address, and so forth and so on. And that we will increment to the next address. And since addresses are all 2 bytes long, we are going to increment the register by 2. And therefore it advances to the next address in the table. All right, you ready? Auto decrement. Well, that's like auto increment, except we decrement the register. We're going backwards in the table by 2 or 1, depending upon the operation. Some operations are 1 byte, some are 2 bytes. And the amount will be determined by the operation. Then we got auto decrement deferred. It's like auto increment deferred, but we decrement. We notice we decrement first. Yeah, I didn't mention that up here. We decrement the register, then use it. Whereas up here, slightly different, we do the increment after we use it. So there's a post-increment here, and there's a pre-decrement here. Doesn't that sound like C? It is claimed, however, that C did not pick it up from the PDP-11. The 11 wasn't really around when the original language B, as it turns out, was developed. It's one of those urban myths in computer science that the plus plus and minus minus operation in C and in other languages came from the PDP-11. It sure looks like it, but in fact it's not true. But it does work the same way. So it's a pre-decrement and a post-increment. In the case of auto-decrement, we decrement first by 1 or 2 because it will be the address of the actual operand. In the auto-decrement deferred, we decrement by 2, again because we're going through a table of addresses out in memory, and then we use it as the address of the address. All right, now we get fancy. Index mode, mode 6. The register plus X is the address of the operand. Well, what's X? X is hidden. Now, the instructions are X will be an additional number of bits following the initial 16 bits following the instruction. As you can see it down here, the index and index deferred mode, X is a 16-bit value taken from the second word of the instruction, from a second word. In double operand instructions, both operands, you can use these modes. So what that basically means is if I've got an instruction, mode 0 through 5, the address of an operand is completely contained in those 6 bits. But when I go to mode 6 and 7, it's not only the register specified, but it's a 16-bit quantity following the instruction. And there can be 2 16-bit quantities following the instruction if it's a 2-operand instruction and both of them are using index or index deferred. Now in the case of index, the register plus the value of this X, this 16 bits. Take these 16 bits, they're following the instruction, and the contents of register N, whatever register N is, adds them together, and that's the address of the operand. In the case of index deferred, it does basically the same thing. You take the sum of the contents of the register and the 16 bits that are following the instruction, add them together, and that is the address of the address. In other words, you go out to memory. This will take you someplace in memory, and those 16 bits in memory are the address of the operand. So index and index deferred all have an additional 16 bits following the instruction. And if the instruction's a 2-operand instruction, and both of them use one of the index modes, there will be 32 bits following the instruction. So the instruction in that sense can be variable length.